This is lecture outline 3. We're going to start with Roman numeral 1, how to read and write chemical equations. They're often called chemical equations because of the math we do with them. We will also call them chemical reactions, of course. And my abbreviation for reactions is RxNS. And it's here that we talk about our first reaction type. These are called combustion reactions, burning reactions, or complete oxidation reactions. Like Eskimos, who are purported to have many words for snow because snow is such an important part of their lives, we have at least 3 and probably more ways of referring to combustion reactions because they're so important to us. For example, the combustion of propane, where I give the formula here. For me, that is particularly important because I use propane to grill foods. And I had a propane stove at my last house, so I was using propane for that too. And combustion is often used to generate heat, to cook things, and those are important things as winter is coming to Maryland eventually. I know it's pretty much still summer as I'm making this. All right, so here we are, combustion of propane. Whenever you write a combustion reaction, then you have here sort of Mad Libs for chemistry, where the thing that goes on this line is whatever is going through the combustion reaction. It is mixed with oxygen gas, and leave a little space here, leave a little space between each in front of each formula, because we'd have to balance this reaction. The products are going to be CO2, carbon dioxide, and H2O, which is water, and actually, it won't be water this time, so I've scribbled out the L for liquid, and I've put gas there. And the reason I put gas there is because this will happen typically at high temperatures, and high enough temperatures that H2O will be water vapor, or H2O gas. So the thing that's being burned today in this is propane, and it's written here sort of in its structural formula, and I want to write it more in a molecular formula or empirical formula. I add up all my carbons, I add up all my hydrogens and put them together. I end up with C3H8. That is a gas typically when it's burned in my grill. Now, all right, so this is a reaction. It has propane plus oxygen goes to carbon dioxide plus H2O, water vapor. Now, what I need to do is I need to balance this. And so far, we can tell that it is not balanced because there are 3 carbons on the reactant side, and there's only 1 carbon on the product side. Now, my guidelines for balancing a chemical reaction are going to be given here. And what I should tell you is there are many ways to balance a chemical reaction. I don't know how Khan Academy does it, but you might want to check it out. Lots of students have found them to have good ways of teaching chemistry as well. And as long as I can follow your work, you can balance reactions and do all of your work in this class however you'd like. Now, guidelines for balancing a chemical reaction. First thing I do is I put a line in front of each compound for the coefficient. And the coefficient, and what I mean by that is I'm going to draw some lines in front. And I know I'm finished balancing a chemical reaction when all of these lines have numbers on them. And sometimes the numbers are 1, and that's fine. Now, I'm going to switch colors here. 2 is going to be put a 1 coefficient. In front of the most complex formula. And what do I mean by most complex? Typically, the most kinds of atoms and the most atoms. So for example, oxygen only has one kind of atom. Those are oxygens, so one element. So propane, carbon dioxide, and H2O, water vapor, all have two kinds of atoms. And then propane has 11 total atoms, so it ends up with the most. So I'm going to put a 1 right there. And that means there are now 1 times 3 carbons on the reactant side and 1 times 8 hydrogens on the reactant side. So I don't know what numbers I have of the rest of them yet because they don't have numbers. 3. Balance the elements in the most complex formula. And I'm going to do this in red. So like I said, on the reactant side, and specifically in propane, I have 3 carbons, which is 1 times 3. I have 1 carbon in carbon dioxide, and I need 3, so I put a 3 coefficient in front. Now my carbons are balanced. Next, I will do my hydrogens. I have 1 times 8, or 8 hydrogens. Hydrogens come 2 at a time, so whatever number I put here times 2 must equal 8. So I'm going to put a 4 there, and then I double check. 4 times 2 is 8. 1 times 8 is 8. And the reason I can directly go to H2O is because it's the only place that there's an H on the product side. So I have to balance the only place there's H's on the reactant side. And you can see oxygen is more complicated. In fact, guideline number 4 is balance element only formulas last, or balance one element formulas. Balance one element formulas last. That's because now whatever number I put here, it only affects the number of oxygens. It doesn't affect any other elements. So you can put whatever number you want here to balance things out. Now for oxygen, let's see. I have 0 oxygens here. So let's just cover that up for a minute. I don't know how many here. That's why I need a coefficient. I have 3 times 2. I have 6 oxygens. And I have 4 times 1, I have 4 oxygens. So on the product side, I have a total of 10. That means I need 10 on the reactant side. Oxygens come 2 at a time, so I need a 5 here. And I double check, 5 times 2 is 10, and that equals the number of oxygens on the product side. So that's my approach to balancing reactions. Let's try 1 or 2 more examples on the next page. Let's try combustion of ethane. And if this were a quiz or exam, I would give you the formula for ethane. And the formula for ethane is C2H6. So burning reaction. Blank plus oxygen goes to carbon dioxide plus H2O. In this case, it's ethane, C2H6. And not that you would know it, but it is a gas. My process, put a 1 in front of the there's my line there. Put a 1 in front of my most complex formula. Balance the carbons with a 2 in front of carbon dioxide. Balance the hydrogens with a 3. 3 times 2 is 6 hydrogens. And I have 6 hydrogens on the reactant side. Finally, figure out my oxygens. On my product side, I have 4 oxygens plus 3 oxygens. That adds up to 7. No oxygens in ethane. I now need 7 oxygens when oxygens come 2 at a time. I need the number 7 halves, or 3.5 there. That is a fraction. Fractions are not allowed in balanced chemical reactions. And so we must multiply this entire reaction times 2. So for fractions, must clear them to get whole numbers. Okay. So put a little star there, put a little star there, so we know that those two are together. And then everything in this reaction will be multiplied times 2 because I have a 2 in the denominator. That'll take care of things. Times 2, times 2. And now that means my final answer, and I'm going to start way over here, is going to be 2 ethane, 2C2H6, plus 7 oxygens, goes to 4 carbon dioxides and 3 water vapors. Oh, sorry, 6 water vapors. That is my final answer for the combustion of ethane. I will leave the combustion of propanol to you, and we are going to do this example down here, which is pretty complicated. Let's see. Also because it has a third product, but we'll work that in. So blank plus oxygen goes to carbon dioxide. All right, I did leave enough space there. There we go. Put the thing, in this case, nitrobenzene. And I'm not sure what the phase of that is, so I'm going to leave it out, but then I am going to put in my lines here. And as you can see, almost every single time, the thing that is being burned or going through combustion is my most complex thing. And so I put my number 1 there. Let's see. As you can see, I have 6 carbons. Therefore, on my product side, I must have a 6 for my carbon dioxide. I have 5 hydrogens. Hydrogens come 2 at a time, so I need 5 halves here. 5 halves times 2 is 5 total hydrogens. That balances. And, I forgot my line. For my new product, my nitrogen dioxide. And think of it this way, if you have any other elements in this compound, there will be products of the combustion process involving those elements, and I always tell you what they are. Okay, so now let's see, yes, everything's balanced except oxygen. For this, I'll do it in red. I have 12 oxygens. I have 5. Do I have 5 oxygens? Yes. 5 oxygens. Oh no, I have 5 halves oxygen because 5 halves times 1. So plus 2. This adds up to 14, 15, 16, 16.5 oxygens. And on my reactant side, what's different about this problem than previous ones is there are 2 oxygens here. And that means that I need 16.5 minus 2, or 14.5 here. And since oxygens come 2 at a time, I need 14.5 divided by 2 as my coefficient for oxygen. So that does balance it, and the way I do it, you balance it, then you clear fractions. So now that everything's balanced, and I can see I have 14.5 divided by 2, which is also 7.25. I see that 0.25, which means there's a quarter in this problem, however you do it, and it means that I must multiply all of the coefficients times 4 to get the smallest whole numbers possible. some of the numbers will be quite large now, but they will still be the smallest numbers possible. So, after all that, these parentheses are just multiplication parentheses. Multiply everything times 4. That gives me 4 nitrobenzenes. Plus, well, 4 times 7.25. I know, right? Get out the calculator for this. 7.25 times 4 is 29. I have then 24 carbon dioxides plus 5 halves times 4. 5 halves, let's do this again. 5 divided by 2 times 4, that's 10 H2Os. And 1 times 4 is 4 NO2s. That is the balanced chemical reaction for the combustion of nitrobenzene. And that is by far the most complicated example that you can see on a quiz or an exam. You're much more likely to see one of these previous examples or something similar. Roman numeral 2. How does a reaction translate into English? Well, just so we have it on this page, I'm going to write the combustion reaction from the last one on the top. That's going to be for propane, by the way. So C3H8 is propane. Add 5 oxygens. And you will produce 3 carbon dioxides and 4 water vapors. Okay. And we could have chosen any of them, but this is nice because it's got a lot of different numbers in it. There's what's called the atomic or molecular meaning of the reaction, and this is very true. On a very real basis, we can talk about 1 molecule of propane or 1 molecule of C3H8 reacts with 5 molecules of oxygen and so reacts with, or 1 molecule propane added to 5 molecules of oxygen. So reacts with or added to is what the plus means. To produce, or reacts to produce, that's just right, to produce 3 molecules carbon dioxide and 4 molecules H2O. We don't have any atoms in this reaction, so but we could. And the idea is you're thinking about atoms and molecules. And part of the reason we only are allowed to have whole numbers in this reaction is because there is no such thing as a half molecule. And we want to make sure you know that. So you won't balance. So there is no such thing functionally as a half an oxygen, especially in this reaction, let's say. Okay, so that's how we translate this reaction into English on an atomic or molecular scale. For the mole meaning, we are going to replace the words molecule with moles, so 1 mole of propane. Reacts with 5 moles oxygen. To produce 3 moles carbon dioxide and 4 moles H2O. To produce. That's the mole meaning, and it is the mole meaning which we will now use to make unit conversion factors based on reaction. And so the first one we're going to do is we're going to say 1 mole of C3H8 reacts to produce 3 moles of carbon dioxide. So all we've done is we've taken part of that statement from the previous slide and we've written it out without the rest of it. And so the unit conversion factor is based on the reactions, and what I'm going to write here is 1 mole C3H8 reacts, and then I'm going to write per 3 moles carbon dioxide produced. So and this is the exact same meaning, this right here, this fraction, or this per statement, as this statement here. 1 mole C3H8 reacts to produce 3 moles of CO2. Can also be stated 1 mole C3H8 reacts per 3 moles of carbon dioxide produced. And this is our unit conversion factor. Using coefficients in the balanced reaction. And we will shorten this. So this is sort of how we think about it, or how I think about it in my head. But we will take all these words out when we do unit conversion factors in future problems. So we will just write 1 mole C3H8 over 3 moles carbon dioxide. And of course, we could turn this into an equal statement as well, and I'm happy to do that in office hours. However, I'm going to go with this approach. We have a balanced reaction. We convert that into a sentence for the mole meaning. We use that mole meaning to create unit conversion factors, which we will then use in problems. So with the balanced reaction shown here, we can write other unit conversion factors. In fact, you can write any combination that you want. For example, 4 moles H2O produced per 5 moles O2 reacted. And these, remember, if you can write them one way, you can flip them and write them the other way, depending upon how you want your units to cancel out. And so any and all possible combinations of these can be used to solve problems. And these are what I call mole-to-mole coefficients, and mole-to-mole ratios, because it's 4-to-5 or 3-to-1. And mole-to-mole ratios always use coefficients. And I'm going to abbreviate coefficients in the balanced reaction. So no balanced reaction, this process falls apart. Let's pause there.